Ray.
Dear God, thanks for a chance to come back together and hopefully learn a bit more about your creations, about how you build logic and numbers to work. Thank you for the apparently good scores that you seem to have blessed us with on this test. May you be helping us to continue to follow you and to seek you in academics and beyond. Love you, Lord. Amen.
Amen. Statistically speaking, Luke is correct. The average on this test is a little bit higher. That's good. Now, I'll give you the test backs later. I think we should probably talk about the homework for most of today, though. Huh? So you guys got questions about Mission 7? Yes, Mr. Gibson. Number 97? But did I say anything about Green's theorem in number 97? I mean, I guess you well, I don't know if you could. I mean, problem 97, you're asked to calculate the integral along some curve of f dot dr, but the thing is, the curve, so f is equal to 3x squared plus y, comma 3y squared plus x, and you're given that the curve has x equals to 2 plus 3t squared, and y is equal to t cubed minus 1. And that's for 0 less than or equal to t less than or equal to 1. That's not a closed curve, so I don't think we can apply Green's theorem, at least not without a lot of not without some thinking. How should we solve this problem, guys? I mean, there are two ways. The first way is just direct calculation, right? So you can just calculate from the definition of the line integral. How would that go? Right, so we do. Okay, so that's c of, let's see, we could look at it this way, 3x squared plus y dx plus the integral, plus 3y squared plus x dy, right? And that would be the integral from 0 to 1 of what? 3 times 2 plus 3t squared plus t cubed minus 1 times dx. What is dx? It's 6t dt, right? And then plus what? Plus 3y squared, which is 3 times t cubed minus 1, quantity squared, plus x, which is plus 2, plus 3t squared, times dy. What's dy? It's 3t squared dt. There you go. Multiply it out and integrate. Anybody do it? This way? What'd you get? What? That's what I got. Very good. I don't know. We can never. It can't be. We can't recover it. It's just. It was said. It's lost forever now. Whatever number that was. No, it's 120. You should find 120. I found several other numbers before I found 120, and then I found my errors. And then after this thought process, it finally dawned on me that there's a way easier way to do this problem. Can anybody here tell me the easier way to do this problem? I do have the details of this in my solution when I post it, so it's not a bad thing for you to work it out either. Some of you definitely need some work on integration and being careful. Sorry. I made the mistake of grading your last test. Details. What do you guys have against details? Oh, details. Don't mind me. So this is equal to what? The gradient of what function? X cubed plus y cubed plus xy. We have a winner. So all you got to do is take that potential function and calculate its difference at the terminal points of the curve. And we will again find 120. But don't feel bad, Timothy. I did the same thing. And it was painful once I realized what I'd done and the fact that I could have done that. Oh, I could have done that and not done this. Those of you who have done solution number 1 are stronger for it, though, okay? So the other way to do it is say, okay, well, this is really the integral over a curve of the gradient of some little function. Let me call it little f dot dr, right? So I just need to calculate f of the endpoints. What are the endpoints on this curve? T equals 0 gives me what? 2 minus 1, right? What's the t equals 1? How did I find that 2 minus 1? What'd I do? Just plugged in t equals 0, right? Plug in t equals 1, what do you get? 5, 0, right? So that will be somewhat comforting that you can reproduce the 120 in this way. So if I ask you to calculate a line integral on test 4, there are kind of two options, aren't there? Well, I mean, there's a few different options, but one of the things you should be looking for is it conservative? Because if it is conservative, it's very, very labor saving, right? So next question. Multiply it out, integrate.
You have the dt and the...
Yeah. Just factor the dt out to the right if you want to think of it that way. Yes, sir.
Can we want like 99?
So problem 99, I give you like basically 4 points. I'll make up other points. How about 1, 2, 3, 3, 2, 3, 7, and 1, 7. Okay, so here would be a different rectangle. And I tell you that the rectangle is positively oriented. So the rectangle is actually the boundary of R, is the part I've drawn in purple. The shaded interior is the solid rectangle, all right? And the question is something like this. Integrate along the boundary of R. I don't know, SpongeBob function of x plus y dx minus, I don't know, Herbert of y plus x squared dy. The point is, this is p, and let me put a plus here. This is q. So if I apply Green's theorem, what's Green's theorem say? You do the double integral over the rectangle of partial q partial x minus partial p partial y. We proved this the other day, that this is a theorem of integral calculus of several variables. And so with that in mind, I can put pretty much, my point is I can put any function I want. You know, I can put, like I said, SpongeBob of x, because I just differentiate p with respect to y, holding x fixed, right? So SpongeBob goes away, and Herbert, well, Herbert's dead, because Herbert only depends on y. He's just a one issue Herbert. So he can't survive this derivative. That goes away, and you're just left with what? The double integral over r of, what we got? We got 2x minus what?
Y.
Not y, but 1. It's okay. And then we integrate over the appropriate, I mean, this is a rectangle, right? So you got 1 less than or equal to x, less than or equal to 3, 2 less than or equal to y, less than or equal to, man, that coffee is rank. You're right. It's really awful. I mean, I haven't been able to smell for about 2 weeks, but it's starting to come back. This is not the right thing to come back to. I want my cold back. Let's see here. So integrate from 1 to 3, integrate from 2 to 7, 2x minus 1. Which one comes first, dx or dy, as I've written the bounds? This is important. dy? Okay. And then dx. So there is no y dependence on that integrand. So what it amounts to is the first integration is just going to multiply by the length of the integration region. It amounts to multiplying by 5. So I've got 5 times the integral from 1 to 3 of 2x minus 1 dx. Because again, dy integrates to y evaluated from 2 to 7. 7 minus 2 is 5. So we're left with 5 times x squared minus x, evaluated from, bounds going 1 to 3. Let's see here, 5. So that's 9 minus 6 minus 1 parentheses minus, so that's 0. And, oh, yes, thank you. So we're left with 30. Anybody work out the one in the notes? I mean, in your actual homework, what'd you get? You got 0? Yeah, I also got 0. Kind of disappointing. Sorry about that. But that's a quirk of the curve. Is this a conservative vector field? The one in your homework. Hyperbolic cosine of the square root of x plus 3 plus y plus 3 plus x squared. Well, if you calculate the curl of that, right, the curl was 2x minus 1, if I recall correctly. 2x minus 1 is not, the z component of the curl is 2x minus 1. You can see that function, that vector field is not conservative, and yet it has an integral which is 0. Which means if we were to calculate the integral around the rectangle in problem 99, the different legs of the integral, they'd be non-trivial. They just happen to cancel, most likely.
So in other words, you got lucky with the numbers you chose.
Yeah, or unlucky, depending on how you want to look at it, yeah. I often have this problem. I make up problems and they work out to 0. It just happens sometimes. I don't want it to happen. It just happens. Other questions? Yes, sir.
Just a short, this is just basically clarification.
Mhm.
On 105, the force of friction equals negative v vector.
Uh-huh.
And then you said where v is your speed.
Right.
Where is v?
So fair question. Problem 105. The relation between the speed and the unit tangent is this. The velocity is speed times the unit tangent. So that's where the speed is. But actually, I think the earlier version I'd written of this problem, I had a velocity, a speed-dependent friction force, and it's a remnant of that problem statement. But no, the speed doesn't. It's not in the force of friction here specifically, but.
Then that's just trying to figure out what exactly. But then problem 104.
Mm-hmm.
What it really came down to is there are a lot of different curves going clockwise and counterclockwise. Could you review that concept just very briefly?
Yeah, I can work. Here's a problem like 104, but not 104 itself. So suppose I had some region like this. All right, and suppose that the outer edge is, say, counterclockwise oriented. All right, and suppose you've got some holes in this thing. All right. Now, in that problem, I mentioned that the vector field is locally conservative. What I mean by that is that the condition that the curl is 0 is met everywhere inside the region that's shaded. So suppose this likewise has the condition, as we're looking at the vector field f equals to pq, two-dimensional, okay? So suppose we have throughout the, ignoring the holes, but between the outer curve C, we have the condition that qx is equal to py throughout, except at the holes. Where the holes, in the holes, it's defined on the interior of C modulo the holes. All right? And again, this condition is what I would mean by locally conservative. I realized that's a term I never defined until this problem. Okay? Now, it turns out that if I'm given the integral of the vector field around the holes, then I can calculate the integral around the outer edge. So suppose that let's say that this hole is, I'll call it H1, and let's suppose it's like oriented this way. Here's H2. I'll orient it the other way. H3 over here, I'll orient the same way as H2. Oops, that wasn't a hole. That was just a diagram. Sorry. Oops. Duh. Sorry. Victim of my own labeling. H3, I'll go counterclockwise. And H4, I'll go clockwise. All right. And suppose that we're given that the integral over, I'm tired of writing, h sub j is of f dot dr is just equal to j, for j equals to 1, 2, 3. That information paired with the deformation theorem is enough to figure out what the integral around the outer loop is. What do we do? Deformation theorem. States that the integral around the outer curve C of f dot dr is equal to the integral. Now, it's equal to the integral, the sum of the integrals over the holes, provided we orient the holes in the same fashion. That's the way it works. So, since I have an outer curve which is counterclockwise oriented, the holes that are also counterclockwise oriented count as positive. Like, that's positive, Oops, but I have to subtract the second one because it's the opposite orientation. This one's also the third one is, the third and the fourth are also counterclockwise, right? As I set it up. So the answer would be, because I'm given that these are equal to 1 minus 2 plus 3 plus 4, so the integral around the outer loop would just be 6, I guess, right? That's a more complicated version of your problem. Now, given that information, what do you think is, well, I mean, let me hypothetical here. I've got a vector field, PQ, right? Here's a point, some point P, and there's some curve like this, C. And suppose the integral over C of f dot dr is equal to 30. Can this vector field be conservative on any domain which contains that curve? What were the list of 4 equivalent conditions we had? Do you guys remember? 1, f is equal to the gradient, right? This list. F is the gradient of little function f on U. 2, path independence. 3, loops give trivial integrals. 4, the curl of f is equal to 0. This assumes U simply connected. And the dimension is 3. In fact, we have more to say about this story in the n equals 3 case. I've really only proved it for n equals 2. These are equivalent conditions. So, if a loop integrates to something non-zero, can it be conservative?
Nope.
No. It's not a tricky question, really. I'm just testing. Were you paying attention when we stated this list of 4 things? And can you internalize that concept? I can tell you the answer for previous years of Calculus 3. The answer is a resounding no. And that makes me sad, because it's not that complicated. Anyway, I digress. You guys are not last year's Calculus 3. You are or previous year's Calculus 3. You are your own people. You are entitled to make your own mistakes. I will not prejudge you. You can make totally new mistakes, or just not even recycle the same mistakes. It's totally up to you. Make no mistakes. Nothing would make me happier than for everyone to make an A on the next test. I would be delighted. My grading certainly would be easier.
Yeah. My dad always said for grading, the ones that go easiest are the hundreds and the zeros.
Yeah. Well, the zeros aren't easy for me. Maybe your dad is a little bit more.
Well, as far as marking on
No,
paper.
you're okay. He is correct. If they're blank, it's easy to grade. That's true. But that also, but it weighs on my heart to see blank tests. Anyway, yes. Other questions, yes, sir. Huh. It seems conceivable that if you understood the lectures I've given recently, and you sat down, you probably could put this homework together in about 3 hours. That seems conceivable to me. Do not assume that that's possible with the next mission, because I don't think it is. This one seems to me a little bit easier than some of the previous missions, and probably easier than mission 8. I would warn you to start working on 8. I had to guess. Okay, so 96, you say? So basically the question is how to find the centroid. So I'll an example somewhat similar would be something like this. X equals to r cosine t, y equals to r sine t, z is equal to mt. You could do this one. This would be the helix. We could say 0 less than or equal to t less than or equal to pi to make it exciting. Because if I do 2 pi, then I know half the things are 0 by symmetry. But if I do pi, then it's kind of a pain. Now, you guys can use a numerical technique if you'd like to calculate the integrals here. They're kind of nasty. All right, I have in the solution, I have a complete solution to the integrals that come up in the problem you asked about was 95? 96. So the problem 96 actually has like integration of e to the 2t times cosine t, right? And I can solve that explicitly without integration by parts. So you can look at the solution for that. But if you want to just use Mathematica or something to do that integral for the purpose of the homework, it's fine with me. It is kind of a nasty integral. It's certainly not something I would want to probably put on an actual test. Okay, so the question then is to find the centroid. And arc length. So basically, if x bar, y bar, z bar is the centroid, does it sound like some kind of like post-apocalyptic 1980s science fiction movie? They're all trying to avoid the centroid, I can just see it now. Sorry, there's this new channel called Comet. It has the most horrible movies on it, like these just long-forgotten science fiction movies from like 1988. It's really, really pathetic television. It's wonderful. But sorry, I was just watching a little bit of something like yesterday. It was so bad. It was just good. Let's see here. Anyway, so x bar, what you do is 1 over the length of the curve, the integral of x ds. Now, in principle, you would have the integral of 1 over the mass of the curve times the density, lambda, times x ds, where lambda was dm ds, right? I mean, that would be, for a center of mass, you would have to do that. But to find the centroid, we just set lambda equal to 1. Assume that we have constant mass density, and that's the nature of this problem, right? But so I won't say anything more about the center of mass here, just to say that it's the same for these. So what's L? It's just the integral, and these are all along the curve, right? Integral along the curve of ds. But what is that? That's the integral from 0 to pi. The speed of this curve is what? Minus r sine t, r cosine t, m. So the speed, which is, by the way, ds dt, is also the square root of r squared plus m squared. So I just have to integrate the square root of r squared plus m squared with respect to time. I get pi times the square root of r squared plus m squared for my example. So let's see here. To calculate the x-coordinate, I would have to have 1 over L, and we know what L is. I'm not going to write it again. And we have to integrate over the curve of x ds. But what's that look like here? Integral from 0 to pi, right? Now what's x? R cosine t, right? Now ds here is fairly simple because it's just a constant. It's the square root of r squared plus m squared dt. Now, for the homework problem you guys have, the speed if you work, and you should simplify the speed. Like, don't leave the speed unsimplified in that problem. That would be very foolish. The speed simplifies down to something nice. It's like, what is it? E to the t times the square root of 3? Yeah. So you should get exponential of time times the square root of 3 for speed in that problem, which is a pain, but it's not too bad. And so, yeah, could be worse. Oh, so that square root of r squared plus m squared cancels with that square root of r squared plus m squared and just leaves me 1 over pi, which is just as much trouble to write as L, so I'll do that. And then I have what? An r over pi integral from 0 to pi cosine t dt, which is just what? As 0, yeah. Which isn't terribly surprising if you kind of visualize the helix going from 0 to pi, right? It starts out at the x-axis, right, and it kind of curves around back up to here. So it's as much in front of the it's as much in the positive x as it's in the negative x, and symmetrically so. So the average x is 0. Y, on the other hand, I expect will be positive. Because if you look at this, sine is positive from 0 to pi. Yeah, z better be m, I think m pi over 2, but yeah. We got mt square root of r squared plus m squared dt. So we have, again, m over pi, because this cancels with the L to leave me pi. M over pi. Oh. Well, maybe, well. Huh. So I get t squared over 2, right? So what's that give me? Oh, m pi over 2 as we thought. Okay. So basically, and if you look at this like this, from top down, it looks like that, right? And basically our center of mass, or centroid for this curve, was like halfway up and like right there, some kind of like, so if this is, it's right there. Whatever 2 over pi is, what is that, like point, it's a little bit, I'm not sure, maybe it's a little bit further out, I don't know, somewhere in here. 2 over pi percent of, 2 over pi times 100% of r, that far out along the y-axis is where the, well, above the y-axis in the zx plane, yeah. I hope you see that these formulas are the same as what we looked at for the centroid of a planar region or a volume. And we could soon do the same thing for surface integrals. We could look at a curve sheet and say, where is its center of mass? Or where is its centroid? But in order to do that, we need to know how to calculate the integral with respect to a surface area element. That's the one thing we have left to do in terms of integration in this semester. So, tomorrow. Other questions? Do you want any advice on how to find the A such that the curl of A is equal to B? Yes, please. There are infinitely many answers there. So we're basically trying to solve the equation b is equal to the curl of A given b. So let me try to work a different problem that hopefully makes sense. Let's suppose b is equal to minus y squared x cubed z. Well, I don't want to put a z there. Let's put a y there. Okay, so what I do, hopefully that makes sense. I'm not entirely sure this problem makes sense yet. It's not the case that every vector field can be written as the curl of another vector field. What would rain on this parade? What's a vector identity we know? The curl of a gradient is what? 0. What's the divergence of a curl? Also 0. The divergence of a curl is 0. So if this is a divergentless, I'm probably okay. What's the divergence of b here? Oh, 0, 0, 0. Okay. Probably work. Probably okay. Probably we're okay. I think that's actually not a probably. It's actually a certainty, but we don't have quite the theory yet, I think, to develop that. We're going to, hopefully by the end of the semester, have that, but we're not there yet. All right, so what I do is I do some name calling. I say A is going to be ABC. And then I just try to solve the conditions, just like we tried to solve partial f partial x equals to the first component of the force, and just like we found potentials before. It's just now maybe you can't guess it now. I personally can't guess these. I'm not there yet. Maybe if I worked more of them I could, but I'm not there yet. So what's the curl of A equal to? Here I'll write it out. So I'll write it out with the mnemonic. It's the determinant of x hat, y hat, z hat, partial x, partial y, partial z, a, b, c. And then we just have to, so I'm just reminding us what the definition of curl is. For the z hat, we get partial b, partial x, minus partial a, partial y. Oh, I'm sorry. Excuse me. Strike that. Strike that, strike that. For x hat, I want the x hat one, so I get partial c, partial y, minus partial b, partial z. It should involve the y and the z components and derivatives with respect to y and z for the x component. There's always this kind of duality in each thing in the curl, right? Like the x component involves y and z stuff. The y component involves x and z stuff. The z component involves x and y stuff. Same thing here. Y, excuse me, partial a, partial z, minus partial c, partial x. And then what? Partial b, partial x, minus partial a, partial y. So what do I need to do? In order to solve this problem, I simply need to solve a system of partial differential equations. You're like, but I haven't had partial differential equations yet. I know, and that's true. And you're going to be waiting a long time to take partial differential equations at this university too, as we don't offer a course in it. Well, that's not entirely true. There's some of our differential equations course has partial differential equations, but it's actually okay. We can solve them. All we need is calculus 3 and a little bit of elbow grease here. So partial c, partial y, minus partial b, partial z should be set equal to what? We want this to solve b, right? So the x component, this is minus y squared. So I have to solve this is equal to minus y squared. And I have to solve that the y component gives x cubed, right? So I need partial a, partial z, minus partial c, partial x is equal to x cubed. And I need that partial b, partial x, minus partial a, partial y is equal to y, right? Let's number these. 1, 2, 3. Now my approach to solve these equations is simply to attack them one at a time. So I just pick one, try to solve it. And then I try to then solve the next one in such a way that I don't mess up what I've already done. That's my strategy. So let's pick on number 1. You guys tell me, what would the solution to number 1 be? C equals to what? Or B, if you we'll do B. B equals to what? You pick it, C or B. What do you want to do? What's that? I heard a y squared z. We have a possibility. All right, so let's go with that. Let's see if we can do that. Great. That will solve this, right? Provided what? Yeah, I need C has no y dependence. All right, so then we go then, and I would then go on to part 3, because 3 is the thing that I might mess up, right? 3 becomes what then? 3 becomes, oh, hey, well that's nice. There's no x dependence for B. So I just have what? Partial a partial y is equal to y. So what's that tell me a should be? Yeah, minus 1/2 y squared. So we've solved, yeah, again, that assumes that, what does it assume?
Well, that has no z dependence, so that makes number 2.
Oh, okay, so then go on to 2. What does 2 give us? Oh, 0. 0 minus partial c partial x is equal to x cubed, which tells me I can make c equals 2 minus 1/4 x to the 4th, right? So in total, we learned that we can make a equal to minus 1/2 y squared, y squared z, and minus 1/4 x to the 4th. Yep.
Basically setting one of those partials to 0, solving one at a time.
Pretty much. That's one thing we can do. Of course, I could also do this. That's also a potential, so-called vector potential. A is a vector potential for B. Conceptually, B is a magnetic field. This vector potential is what comes from the existence of a moving current through something called Ampere's law. This is not even in the Physics 232 course, though, unfortunately. What I did, though, maybe you can recognize that A2, as I wrote it, is just A plus the gradient of the xyz function. But of course, when you take the curl of a gradient, it's 0. You can add the curl of any scalar, the gradient of any scalar function to the vector potential and not change the magnetic field which is outputted. There's tremendous freedom in the selection of a vector potential for a given magnetic field. Physicists make various choices of the vector potential corresponding to what they call a gauge condition. This flexibility is used in interesting ways in theoretical physics. But anyway, oh, it's 4 o'clock. Wait a minute, we still have 5 minutes, yes? Yes, sir.
Also, for your A, B, and C there,
Mm-hmm.
you could add any function of x to any function of b, but y to be any function of z.
pretty much. I mean, more generally, you could just add the gradient of any. I mean, this is nastier, right? I even have a function of y and z here in the x part, a function of x and z here in the y part, a function of x and y in the z part, but they're done in such a way symmetrically so as that when you calculate the curl of these new terms, even though they're non-trivial, they will cancel. Woe to the grader on this problem. There are many, many answers. But in kindness to the grader, I showed you a solution, so I'm guessing your solution will somewhat look like mine. And then the grader will be, it won't be so bad. Yeah. If you guys haven't seen Ant-Man already, you should go watch it while you can. TikTok, because it's 19th, it closes. So sad.
How can a movie entitled Ant-Man be good?
I know, right? And yet, it is. You question the title of Ant-Man. So what if it was like, what if it was a movie about the Ant-Man, but it was titled like Spider-Man? Then it would be a good movie?
Yes.
Okay. Wait a minute. Before I can respect your opinion, name for me some good movies. Oh, brother art thou. Where art thou? I think your movie views may be too nuanced for me. Godfather. That's a cop out.
Godfather Bible. Watching Godfather.